Welcome back. In this video I just want to do a quick little exercise to do some problem solving to kind of check this idea, right? So we've just seen weighted A star. We've been kind of presenting it in the lecture material as a better algorithm than A star, right? Hey, we can trade off a little bit of suboptimality if that's something we don't explicitly care about. If we're okay with a slightly worse solution, then hey, weighted A star is consistently substantially faster. However, and because of that in many domains, we would perhaps choose weighted A star. But now that raises the question, obviously, then, is weighted A star always better than the generic A star? The spoiler alert is that it absolutely is not. Weighted A star can still do substantially worse than A star, and I just want to walk through like an idea, try to get some intuitions of in what kind of situations is that going to happen. So now to write down the differences, of course, between A star and weighted A star. Right, weighted A star is defining the f value, so fw of n is equal to g of n plus w times h of n. Now the equivalent, of course, for regular A star is the exact same, just without the w. Okay, so it's this term here that's the key difference. Well, what that means is that we are applying more value, more of a weight. And again, of course, this is right when w is greater or equal to 1. W has to be making the heuristic weight larger, more important. So in these situations, we're obtaining speedups because we can make a little trade-off of optimality in order to boost performance. But let's have a look at that then. What situations is weighted A star actually going to do worse than A star? Well, this is, I think, quite simple and very intuitive. In cases that your heuristic value is not accurate, right? When the heuristic value is misleading you, it's incorrect. Well, then, of course, the more we value that incorrect information, well, it's kind of like a greedy approach, right? You're approaching as W becomes larger, this greedy best first search. Well, that means that you can do worse when you're additionally misled down paths that look promising, into rooms that look promising, but they are not necessary. You cannot reach the goal via those locations. So essentially, weighted A star can do more fill-in than the A star algorithm. A star does already do a substantial amount of fill-in, which is also its own issue. So they're both going to have very, very similar behaviors, but weighted A star, because of this additional W driving the heuristic value, it can actually try to be more greedy and get stuck to a larger extent. So I have a couple examples just to look at. Here we have a very simple start and target. I often ask my students, okay, well then how could I modify this map? How could I draw in walls? That means that we would get stuck. So it's this idea, right, that the heuristic is uninformed. It is inaccurate, right? There's a large error in its estimate of the distance to go. Well, what this means, right, is essentially that there are, even though it thinks it's a pretty straight shot, maybe it does grid distance, right? The grid distance heuristics, these basic heuristics, are not informed about where walls are. So imagine there's a wall blocking the target. The heuristic really thinks we should be going along this diagonal. It really thinks we should be going that way. And so what's going to end up happening is you have this fill pattern as it tries to prove and then works backwards before it finds the detour around the edge. Okay? So that kind of makes sense, but that's similar in both of these algorithms. I think we can make the example a little bit more interesting, a bit more fun, if we modify it such that we create what we often call like a room, right? This is a large area that is enclosed by walls, and this is where the flood fill issue of A star already comes in. In both of these algorithms, in both A star and weighted A star, you're going to have this fill-in behavior, right? You kind of go along this wall and you walk your way back. Okay, now essentially, because we have an additional weight, I'm unsure if you can even tell the difference of the green versus the yellow on the board, but weighted A star is just going to have more fill-in along this frontier. It's even more greedy. It's going to really smash its head against this room. It's like if you've given the W10, I'm 10 times more likely to keep trying to go in these promising paths, in this promising direction. Eventually, obviously, one version of the path will remain. You will find your large detour, but it's going to take a bit of time, and it's only when that weight, when the F values of going the wrong way, right? This is a bad direction. It's when you start stepping this way, your heuristic value is increasing, so it looks worse. So that's a pretty simple example. I think I just want to then, I think this is a decent idea of what's happening on, but then of course A star and weighted A star kind of have this similar flood fill, so maybe it's a little counterintuitive. I just want to prove I've just drawn this up here in a much simpler example. Well, the same behavior is observed, but we can see how this would work explicitly just by doing a simple F-cost calculation. So then let's look at, we have both regular A star and then weighted A star. Weighted A star. All right, so we're starting from the start S to some target T. You see how this somewhat approximates. We have like these blocked connections here, which suggests a wall, very similar to my other example. Let's have a look at calculating some of the F values. And we'll just here use the heuristic of actual just grid distance, because that will make the most sense. So we have A and B, and we're going to look at which version of the path is more promising, the one towards the target and entering this kind of room situation, or the long detour around. Okay, so f of A is equal to the cost of G, which is 1, plus then 1, 2, 3, 4, 5. The heuristic is going to return 5 costs. So this is 6, okay? Then the other way, we have a step of 5. So again, the weights, the costs of the edges could have been different. I think it's just in a very simple example, hey, just ignore the cost of everything else. Just say, just going this way is a higher cost. You're entering the room, you have to like spend some time opening a door, something like this, right? So A star already thinks that's kind of a bad idea, whereas weighted A star really just goes, hey, the door looks like the right direction. I'm absolutely willing to spend the cost. So we have a cost of 5 then plus, so that's 1, 2, 3, right? So from the get-go, A star thinks that A is looking more promising, 6 is smaller than 8. Well, when we do the same for weighted A star, we'll see that it is more greedy. It does not agree with this information. So f of A is 1 plus, well, we have to define some form of W here. I'm just going to define W equals 3. W equals 3 isn't even that large, right? That seems like a pretty regular number. Hey, the solution could be 3 times worse. Just get me there quickly. So 1 plus 3 times, and then again, it's the same heuristic value of 5. So this is now 16. And then this is a cost of 5 plus our 3, so it's 3 times 3. So 9, 14. Okay, so weighted A star is going to think, hey, this looks good. Whereas A star already realizes that going down the detours would be better. And so ta-da. So the difference in their behaviors really starts to become apparent even in simple examples. Imagine this room, right, could grow in size. Like the larger this is, the more time weighted A star is going to spend bashing its head against the wall. So what was just really important to note, weighted A star is great in practice. When you're willing to trade optimality, it can be substantially faster. But of course, it's not always better. There's usually no free lunch. Regular A star can sometimes be substantially faster than weighted A star because of this additional greedy metric we've built in. So thanks for watching and see you in the next video.